안 들립니다. 안 들려요.
마이크 테스트 안 되네요.
들립니다.
되나요? 예, 감사합니다.
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 Okay, okay, let's resume. So briefly, I was just mentioning that in this series of talks, I will describe some counting problem on mapping class groups, and this time I will try to describe some geometric objects and related facts. So the players of this series of talks is first the mapping class group itself. So this is some sort of the group of homotopic classes of the diffeomorphisms of a surface where for this surface I bring a finite type hyperbolic surface. So you can just imagine your favorite hyperbolic surface and try to generate a non-trivial map on this surface, modular homotopy. So you will not, it's not sufficient to only deform, for example, a contractible part. You should, for example, rotate this surface as a whole to generate a non-trivial mapping class, or you can try to deform the surface along this curve, which is called ventus. And this group is particularly interesting because it arises in, like, for example, the study of three-dimensional manifolds, and it's a part of the Thurston's great program of hyperbolization. And to study this mapping class group, we want to see its action on interesting enough spaces, including first a Teichner space, which is defined analytically, but there's also a companion space called the curve complex. And finally, I will also describe the geometry of the mapping class group itself. More precisely, its scalar graph. Okay, so these are the players. And the thing is, let's first see some the most simple case, the simplest case, which is the mapping class group of sigma 1, 1, which is a well-punctured torus. More precisely, sorry?
Sorry.
Okay. So this mapping class group is more or less like a PSL2 set. And we all know that it acts on the hyperbolic plane. And this is indeed isometric to the Teichner space of the surface. And then we all know the dynamic properties of the matrices. So if a matrix is matrix in this PSO2Z has traces has absolute value smaller than 2, then this is called elliptic, which is which has an action like a rotation around the fixed point. And if the fix is 2, and if it's non-trivial, then it's called parabolic. And this acts like a horocyclic translation. And finally, if trace is greater than 2, then this is called hyperbolic or logarithmic. And this is the elements with the most interesting dynamics, because it showed like it moves the entire hyperbolic plane as a translation with the north-south or single-source dynamics, if you prefer. And it's a common belief that logarithmic or hyperbolic elements are dominant in this group. What I mean by this is, if you classify the elements with respect to this trace, then there are only finally many candidates for this trace for like elliptic and parabolic elements, whereas for hyperbolic elements you have tons of choices. Or if you want to phrase this genericity or dominance of hyperbolic elements in a different way, then there are tons of different ways. For example, counting matrices with respect to either matrix norm elimination trace, or with orbit points. And let's just so the third perspective is like this. You have an action on H2. So if you want to sort out various matrices, then you see their action on this this reference point, and then it will, some matrix will move it much farther than others, and some will just keep it, just unchange it, and then you draw a metrical just to collect some finite number of matrices, and you only observe the matrices that send this point into this matrix, this finite range of metrical, and then among these finite many matrices, you can compare the population of elliptic, parabolic, and hyperbolic elements. And as you increase this radius, you can see the asymptotics of the population. So for this simplest McIntosh group, the situation is quite visible. However, for more complicated surfaces, it's even hard to describe this triangular space or Kerr complex. So initially, people knew that. Oh, by the way, just after finishing this simplest example, is there any question so far? If not, I'll proceed to geometry. So for the simplest case, we knew which space this group acts on as H2, which is classical. And H2 is great because it's having a constant negative curvature. So if you're a dynamicist, if you're observing a dynamics on a constant negative curvature manifold, then it's great because it enjoys some you can just make use of some hyperbolic dynamics. I mean, it's much simpler. But if you're working in a working in a more complicated space, which is only non-positively curved, which may include some flat, like R2 or Z2, and some negatively curved behavior. If you have this mixed property, then it's not evident whether you can apply this theory of hyperbolic dynamics or not. And for Teichner space, unfortunately, just to describe, this is a space of marked Riemann surfaces. So if you apply a mapping class group and mapping class action, then it amounts to changing the marking, but keeping the moduli same. And this space is equipped with either a Teichner metric or verified symmetry. Both are metrics. They're defined from some optimization problem among Riemann surfaces. And then, unfortunately, Teichner space with either Teichner metric or Vepeta symmetry are not strictly negatively curved. So this is a theorem by, I think, Mazur and Wolf, and also independently by Ivanov. So this is not uniformly hyperbolic. If sigma is complicated. To spell this out, if sigma is not either one punctured torus or a four punctured sphere, if sigma is more complicated than that, then a Teichner space is not, with Teichner metric, is not hyperbolic in some sense. However, people didn't really give up pursuing this hyperbolic dynamics. So they wanted to construct a new candidate of space having uniform hyperbolicity. So that was the idea of Mazur and Minsky. So out of this Teichner space, they deformed the space in a pseudo way to obtain a uniformly hyperbolic but non-proper space, which is the curve complex. So the relationship between Teichner space and curve complex is something like this. So here's a Teichner space. And unfortunately, it has a bunch of flats. I mean, it's fair to say that it's non-positively curved in a grand scale, but it contains a large scale flats where partially coming from the commuting elements of vector classes. And then they wanted to contract all those flats in a nice way to generate a hyperbolic structure like a real tree. So they wanted to generate some graph, something like this. And one way to do this is to contract all these thin parts. to describe. So each point of the Teichmann space is a Riemann surface, a marked Riemann surface, and some Riemann surfaces have very fat property. So some Riemann surfaces are looking like this, whereas some Riemann surfaces are looking like this, with very thin waist. So these are called thin, and these are called thick. And for thick parts, this is one example of thin Riemann surface. But you can also consider this kind of thin Riemann surface, where you can see disjoint curves that are simultaneously thin. So you can first generate a thin Riemann surface like the original one, and then you can generate a simultaneously thin Riemann surface, and then you can go to this one. So if you consider this kind of continuous deformation, then you can move from one thin surface to another thin surface having distinct waist. So if you pinpoint, if you label thin parts with the waist curve, then those thin parts are overlapping. So these joint curves can overlap. And then if you contract each thin part as a point, then these are connected like an edge in a graph. So, but intuitively this way, if you contract all these thin parts one by one as a vertex, then you will get a graph. This is a graph where vertices are curves on surface, and you draw an edge if V and W are. So if you made this thin, then you cannot expect any curve intersecting with this curve to be thin. This is actually not hyperbolic geometry. Here, this is Riemann surface theory, but there's a lemma like that. If this is thin, then any curve crossing this curve cannot be thin. So you draw curves only if those curves are disjoint. Then they can be made simultaneously thin. So if they are disjoint. So out of Teichmann space, by this deformation, they made a graph. By the way, this graph was already there. This is due to Harvey. But what's surprising is measurements can prove that this graph is hyperbolic. However, the cost of making this hyperbolic complex is that non-proper, being non-proper. Not locally finite. And you can see this because if you have a curve, and if you try to draw edges with any curves disjoint from this, then this curve is one candidate, but here's another one. And if you twist this curve around this curve, then you get another curve that's also disjoint from here. And also, if you deform whatever within this part, this subsurface, then you will get infinitely many curves that are disjoint from here. So this graph, in this graph, each vertex is connected with infinitely many other vertices, which makes it hard to apply arguments involving like finiteness. So these are two. And finally, actually, this is really important. The group mapping test group has an isometric action on, sorry, probably. has an isometric action on Teichmüller space. And you can make this deformation equivariantly with respect to this action so that you also have an isometric action on this curve complex. So perhaps we can pursue this kind of strategy, like acting on either Teichmüller space or this better curve complex. There any question?
You're using the distance on the graph.
Yeah. So when you draw this kind of metric ball, then you can either draw on this Teichmüller space, or you can make use of this distance on the graph and draw the ball.
When you say thin, is there a definition of thin?
Yeah. So this is a Riemann surface, and for each curve alpha, you can imagine a topological cylinder embedded in this pi1 injectively embedded cylinder on this surface, Riemann surface, and then this surface is, by uniformization, this is conformally equivalent to a finite cylinder on just standard cylinder on the complex plane. Then the ratio between this and this is called the modulus, and you seek for embedded cylinder with maximal modulus. And if that modulus is large enough, it means that you have embedded very long cylinder in this surface. Then you call this curve thin. So based
large enough, that has a definition.
So you pick an arbitrary threshold first. So if you say it's epsilon thick, epsilon thin, then you can embed this kind of cylinder with here circumference 1 and here 1 over epsilon.
So the definition of thin depends on that definition.
Yeah, definitely. So there's what's known as, it's not good enough to collapse these thin parts for arbitrary threshold. There is an epsilon 0, which is I don't know the value precisely, but if you take an epsilon, whatever epsilon is smaller than this epsilon 0, then the deformed space will enjoy a good property. And this is related to the Margulis constant. More precisely, this constant is such that you cannot detect a curve and another curve intersecting with this curve to be simultaneously epsilon thin. So there's a known constant called Margulis constant, epsilon 0, so that you cannot expect having an edge between intersecting curves. Okay. So before describing the dynamics of Benton class group on these geometric objects, I will describe this kind of partial hyperbolicity. Like if you collapse this, if you ignore this flat parts, then it becomes hyperbolic. But there's another way to describe this kind of phenomenon, which is called the contracting property. So in H2, if you draw an infinite geodesy and another ball that's disjoint from this geodesy, then its projection onto this, if you take the nearest points from each point of this ball to this gamma, then you will see this kind of shadow. And the size of this shadow is uniformly bounded. So if you bring whatever ball, the smaller the ball is, the shadow will be smaller. That's true. But it, like however large you bring this ball disjoint from this gamma, and if you project it onto this gamma, then it will have a uniformly bounded shadow. And this is owing to this kind of curvy like geodesics drawn on the hyperbolic plane. And you can expect the same thing for manifolds with constant negative curvature, or the negative curvature is bounded away from zero. Then you can expect pretty much the same phenomenon. But if you have a flat, so on R2, if you draw an arbitrarily large radius ball, and if you present a geodesic disjoint from it, then the shadow has exactly 2R, size 2R. And if you increase the size of R, then there's no uniform bound, right? However, if you think of a mixed space where you have this kind of flats, but these flats are actually connected with some tree, connected like a tree. So you have some places where flat geometry comes in, but you also have this kind of tree-like structure in between. Then if you draw whatever, like however large bowl here, if you, like here's a tree, and if you project it onto a tree-like direction, then the projection will be just a single point. So in some sense, this direction can suppress the flat dynamics happening here. So if you can just witness this kind of, secure this kind of directions, then there's a hope that some hyperbolic behavior might appear. So hence, we define a property. So X is a space, like, let's say, diagonal space. A subset A is contracting if there exists a uniform bound such that any metric ball disjoint from A has bounded diameter of the projection of this ball onto A is 1. And it's a theorem by Minsky that peak geodesics are converging. So although there are lots of theme parts lurking around here, if you can draw an infinite geodesic that's not passing through any of these blue regions, then if you project this kind of flats onto, like, if you project any ball that's drawn disjointly from this gamma, then it will have bounded shadow. And we'll soon see that some certain mapping classes are associated with this kind of big geodesics. And we can realize this kind, we can make use of this contracting property while studying the mapping class group action. And but here's a caveat. Here I wrote like any balls disjoint from A. But if you imagine this kind of property on some space X. And if you deform the space X into another space Y, like you did for between Teichmann space and curve complex, if you deform it like this, then the metric ball is deformed. You employ different distance, and this geodesy is also not a geodesy. But if you recruit, for example, quasi-geodesy, then probably you can say pretty much the same thing. But this ball is like deformed. So considering this kind of deformation, probably it's better to mention like this. You have a ball whose center is away from this gamma by d, and if so in this space Y, what I expect is if d is greater than kr, or some k greater than 1. If d is, for example, more than the double of r, more than twice of r, then this ball of radius r, centered at x, has bounded shape. So for this space, for example, for Teichmann space, you have the perfect contracting, but perhaps on another space which is somehow deformed, you may not expect the same phenomenon, but you can perhaps expect a partial scenario where you cannot expect this R to be as large as D, but it's, for example, it can be as large as like 0.5 D or something like that. Then you have bounding projection. You may require this kind of axiom to a deformed space. And this deformed space will be yet another geometric object, which is the calligraph of mapping class. So the goal of today's talk is to explain that this is the work of Minsky, and a relevant fact for the calligraph of the mapping class group is done by Duchin, Rafi, that on the calligraph certain geodesics, I will say the orbit of okay, so for this property, I will say contracting, and for this property, I will say weakly contracting, and I will spell out the definition here. The orbit of certain mapping classes called pseudo-Anosov. It's weakly contracting. It means that, let's say, P, and orbit of I, if for X in the calligraph, and with distance from X to the orbit projection of the metric ball of epsilon d, perhaps not epsilon, I'm sorry, rho d of x onto this orbit. And I didn't really explain how this perfectly contracting property on Teichmann space can imply this weakly contracting property on the mapping class group. I didn't explain that, but perhaps it's good to first spell out this statement, and then if time allows, I will go into the details. So pictorially, you imagine only this metric ball to have bounded shadow, but if the radius is totally huge, then you have no control on. You give up the control of the size of the shadows.
What are the dependencies of M and rho on the parameters?
So here, first, if you define a calligraph of the mapping class group, you first pick finite generating set. So it definitely depends on the choice of generating set, and it also depends on. So here, this is an orbit of arbitrary reference point, and it depends on this reference point. That's also true, and it also depends on the H of the pseudo-Anosov. So M and rho are depending on this phi O and the generating set defining this calligraph. But other than that, it's not depending on this X. It's uniform for all space, all points in the space. And I forgot to mention that remark. In hyperbolic spaces, such as the curve complex, this kind of contraction property holds for all geodesics. Enjoy the contracting property. With uniform bound. And that's pretty much equivalent. So if I have a geodesic space where all geodesics are contracting, like if you project any ball disjoint from any geodesic, then you have a uniform bound, then that space is actually hyperbolic and vice versa. So that's the ideal situation. But in mapping class group or in Teichmann space, you cannot expect that, and you only expect that for certain geodesics or quasi-geodesics. So in the remaining time, I will describe basically how this is proven. And this is the ingredient that we will use in the next talk. So the geometry of both the curve complex and the calligraph of mapping class group is quite bizarre, and also Teichmann space. And for example, if you want to describe a distance from a point on this Teichmann space, so here this is Teichmann space, and if you want to describe the distance between x and y, so this is surface, marked surface, and you project it onto the curve complex by putting the thinnest curve, the shortest curve here, then you will have a projection here and here. But obviously the distance is deformed. So the distance between this and this here is not equal, or they are not even roughly equal, because perhaps you can bring this curve into another curve by, for example, a mapping class group action. But keeping this here, keeping this pretty much the same, you can also deform only within this part, just keeping this. And then you can expect some further progress on the Teichner space. So in this way, the displacement on the Teichner space is not honestly visible in the curve complex, but it can also entail some extra deformation happening in the subsurfaces. So each surface has lots of subsurfaces, and there's a systematic way to just order them. That's too complicated, but I will only describe this distance formula. So on this Teichner space, if you bring x and y, if you assume that x and y are both thick, then this is coarsely equivalent to the distance on the curve complex. So this is on the Teichner space of sigma. This is pretty much the same with their corresponding curve complex distance plus all the deformations on the subsurfaces. Taking sigma here is unfortunate, but cy xy with the modification. There should be a threshold. I mean, there are infinitely many subsurfaces, and if you take this sum, then it can be an infinite sum. But if you only sum the distances on the subsurfaces, having so precisely it should be sorry, this is a tiny detail, but if you set a threshold to k, and if the value is smaller than k, then you suppress. This is a function f, and you put here by x. Yeah. So the precise theorem is there exists a threshold k such that this summation coarsely tells you the distance here. Oh, sorry. Here I think this should be log. No. Plus there's yet another. So the smallest subsurface is the annulus that you can embed on the surface. And for these curves, the annulus around the curve, you have some peculiarity. This is a peculiarity for the base case. And here you require this. You add log instead of just plain. This is a Teichner space distance. And for mapping class group, I think you're not requiring this term to be log, but this is just plain, just distance. And so if you only see their projection on the curve complex, it may not be honest, because you have tons of vectors coming from the subsurfaces. But the thing is, if you have a long contribution from this part, then these parts are suppressed in some sense. And if you have a big enough contribution from one of them, then all the other contributions are small. So this is some sort of orthogonality between the vectors. So this can be viewed as different slots, different coordinates of like L1 space. And then one is just standing out. And if one is standing out, then the other terms are not contributing that much, actually. So using this, I want to describe the situation here. So for on curve complex, you have the perfect contracting property, but on mapping class group, you may not have. So suppose you have the pseudo-Anosov axis, and you try to show that if this is a small enough ball, like this is D and this is rho D, you want to show that this projection is small. And then you first bring this situation to the curve complex of the entire surface, not the subsurface. Then perhaps this distance might be, this can be perhaps comparable to D, perhaps KD. And this one cannot be exaggerated. Like it can be shortened, but it cannot be exaggerated. So if you can secure certain ratio of D, then the corresponding the radius of this deformed ball is still some sort of like K prime rho D. Then since the curve complex is hyperbolic, it has a contracting property and you have the bounded shadow. But suppose that this is tremendously shortened, let's see. So this is scenario 1. And the second situation is this distance, there's X and I will draw it Y. X, Y. Here, X, the distance between X and gamma is tremendously shortened, but you have Y here. So this distance is large. Still, Y could be here so that it may have a small projection. That's fortunate. But perhaps Y might have progressed till here. Then this means that this geodesic is actually fellow traveling some part of gamma. It's coming close to here. And what you can now show is the other what you can show is what was that?
You still want to show that Y is far from gamma. Right?
So
This is false if Y is on gamma, for example. So
yeah.
You want Y to be far.
Yeah, that's true. That's true. Yeah. So I want this distance to be, so if this happens, then this distance is too close to here. But I want to claim that this is not the case. Hence the conclusion. As far as I recall, yeah, now I see. So this distance is shortened, which means that among this presentation, this part is not contributing that much. Hence, you have contribution from here. However, if you have, so for this distance, you have contribution from this one, but whereas the distance for the distance formula from Y to gamma, the corresponding terms are considerably shorter, smaller, because, yeah, that's basically how it's proven. Sorry, I cannot spell out all the details, but yeah, perhaps I forgot the last piece of the detail, but this is how this distance formula relates the contracting property on the curve complex with the mapping class group, although partially. So here, the vector of rho is necessary here. And since the distance formula is depending on the choice of generating set of mapping class group, hence the dependence of rho to that. Okay, I'll stop here, and next time we will begin from, we will describe the main problem, and we will describe the relevant developments on the theory of random walks on mapping class group using this kind of property. I'll stop here.
Thank you very much for the talk. Are there any questions or comments from the audience or from the audience in the Zoom?
I have a question.
Okay.
In the first line, you say little x and little y. Those are points in the type of mission.
Yeah.
On the second line, you also use x and y as a point.
Basically I was using some abusive notation. So what I mean here is, let's say, so here the convention is you fix a modulus, like you fix a point, reference point O, then if you move it around Teichmann space using the mapping class group, using the mapping class, then you can just regard this phi O as X. And then here, what I put is actual phi. So that's the abusive notation that I use here. So here it should be phi and phi prime. Then the corresponding thing is you fix a O, you fix a Riemann surface, and then you plug in phi O and phi prime O. If you compare these two formulas, and here it's yet another choice of curve made on this surface, and then you put alpha here, and you put phi alpha and phi prime alpha, something like that.
Probably it will be instructive to see the comparison of these three metric spaces with this Teichmann space,
Yeah.
Cayley graph, and curve graph. So Cayley graph is subspace of Teichmann space, right? By taking an orbit.
Yeah, but with different metric.
Right. The metric is different.
Yeah, the metric is
And then, but it is subset. So you
Yeah,
can
that's
realize
true.
it.
Yeah, that's
But its isometric actions is like mostly embedding.
That's true.
And also, from the Cayley graph to the curve graph, you just simply cone off dentist centralizers, right?
That's
Just
true.
graph theoretically.
Yeah.
So that's how you pick a curve on the curve graph.
Yeah.
Right? So for each dentist cosets of dentist centralizers,
Yeah.
you just declare that they have distance one among each other.
Yeah, that's true.
One among each other.
So here's the Teichmann space, and you first pick a surface, and then you try to generate its translates by mapping class group action. Then if you can move from here to here by a generator, then you draw an edge. If you draw in this way, then it will become the Cayley graph of the mapping class group. And as Sam mentioned, you may have some dent twists. So dent twists are the deformation around each curve. So if you have dent twists here and here, then they commute in some sense. So they correspond to some flat-like structure. So if you just kill those flat-like things, then you will get the curve complex or curve graph. Yeah. So here you kill thin parts or committing dent twists. Then it will become another graph called curve.
It is not invertible process.
Yeah, pretty much. Actually, if you go to the curve complex, then you cannot reconstruct it as a mapping class. You cannot reconstruct a mapping class. If you suppose that your x is here and your y is here, and can you can you declare a single mapping class that moves x to y? Actually, it's not possible because there's a stabilizer. There's an infinite stabilizer here that fixes the curve, but does something non-trivial.
I was just trying to answer Professor Kim's question, explaining the arrow. So you pick a Riemann surface, then choose the nearest Orbi point by the mapping class. Of course, there are choices, but just choose one. And then for the mapping class, you try to see which cosets of then twist it belongs to. Of course, there are choices, but there are only finite many curves that is fundamental domain for the curve reflection. So choose that coset, and then the curve, the resulting curve, is the image of that arrow. So yeah, I guess that explains the arrow when the distance is from there below. Are there any other questions? So if not, let's thank the speaker again. So let's take a 5-minute break and start the Homin list talk. 네, 고마워요. 잘 들었어요. 다음부터는 한 90분 해야 될 것 같은데? 그렇지 않아요?
제가 너무 좀 두서없이.
그게 아니라 그냥 할 얘기가 굉장히 많은 것 같은데 한 90분 해야 될 것 같아요. 한번 그렇게 한번 해볼까요? 그럼 잘 들었어요. 고마워요.